On Earth, if the particles are large enough for us to see them, even under a standard microscope, they're going to sink. And when they sink on the bottom, that we lose a lot of information. And we would much rather, in terms of discovering fundamental physical mechanisms, they need to stay suspended. And we need to observe them in the suspension for long periods of time to make sure they're stable, to make sure the results are repeatable. And experiments on the space station help enable those types of discoveries under those observations that are not masked, that are not hindered by gravity. Currently, right now, we are looking at fundamental interactions between nanoparticles and microparticles. Once we understand those fundamental mechanisms, for example, there's a certain balance, a certain recipe of microparticles and nanoparticles where the nanoparticles will form a halo, similar to a mobile charge barrier. And if you have an imbalance in terms of the pH, for example, or the nanoparticle concentration, then things don't happen as expected. Maybe they adhere to the particle, maybe they dissociate and move away, and then other microparticles interact with each other and agglomerate, and we don't want that. So we haven't looked at specialized microparticles or nanoparticles yet, because we're still looking at the fundamental mechanisms under, we'll say, simplified particles. We want to start simple first before we move on to these specialized particles. One area we would like to apply this knowledge is towards quantum dot solar cells. Why we are interested in that type of solar cell is, first, the standard silicon-based solar cell, its efficiency theoretically can max out around 30%, 33%. Quantum dot solar cells, on the other hand, their efficiency can max out above 50%, I think around 53%. Currently, the current state of the art of quantum dot solar cells, we're around 9%, and there's challenges associated with that. And one of the challenges is arranging the quantum dots relative to each other and relative to other structures. And once you can master where those quantum dots are within that cell structure, then the efficiency will go up. So we hope to use the knowledge that we gain from our International Space Station experiments and then eventually apply that fundamental colloidal interaction to the solar cells, and we'll apply them later on in our research on Earth. Our team at the University of Louisville, in collaboration with the Advanced College Experiments at Glenn, we have a team within the Cone Renewable Energy Center where they work on roll-to-roll fabrication, including spray deposition techniques of solar cells. So when we have a fundamental discovery based on our experiments on the International Space Station, we hope to apply this towards these roll-to-roll manufacturing techniques. And roll-to-roll manufacturing techniques makes the fabrication simple, straightforward, less expensive, and can be mass-produced so we can get it out there to the general public. So this research wouldn't be possible without the involvement of the EPSCOR program, and even more specifically the Kentucky NASA EPSCOR program, because they've helped us with outreach activities as well as facilitating this research and moving forward with this and helping with our collaborations between the University of Kentucky, Western Kentucky University, and other researchers within the state to sort of broadly educate everyone about the impact of colloid science, as well as the research activities that are going on the International Space Station. Part of the mission of EPSCOR and the Kentucky NASA EPSCOR program is not only to conduct research, but also to expand the facilities and research infrastructure within our state and, of course, at the university level. So we've been acquiring equipment. For example, we got a confocal microscope that, of course, helps us observe these colloidal interactions. But we've had colleagues use this equipment and bolster their research. So not only does it impact our research mission with NASA and with the Advanced College Experiments, but the infrastructure that it built to make our research possible also impacts our researchers within our states.